All right, let's dive in. Today, we're tackling a real classic, a problem from Irodov's legendary and legendarily difficult book of physics problems. We're going to break down problem 1.165. It's a fantastic little puzzle that really forces you to think differently about something as simple as a falling rock. So, here's the setup. A stone falls, hits the ground. Simple. The problem even hands us the answer for its impact speed. But that's not the point. The real challenge, the twist, is to prove that same exact result from a totally different and kind of weird moving point of view. You know, if you're just standing on the ground watching this happen, the physics is about as straightforward as it gets. You plug a few numbers into a basic kinematics equation, and boom, you get the answer they gave you. Easy peasy. And this is where the fun begins. What if we weren't standing still? What if our entire perspective, our whole frame of reference, was plummeting towards the Earth at that exact same final speed as the stone? What would the physics even look like then? Okay, let's do this. Before we jump into that falling frame, we're going to quickly run through the solution from the normal stationary Earth frame. This is important because it gives us our target. It's the answer we know we need to end up with, no matter how we get there. So we pull out our trusty old kinematic formula, v squared equals u squared plus 2as. The stone starts from rest, right? So the initial velocity u is just 0. The acceleration a is simply g, gravity. And the distance s is the height, h. You plug those in, rearrange it a little, and you get that classic result. V0 is the square root of 2gh. No surprises there. Okay, now for the cool part. Let's completely change our perspective. Imagine we're in an elevator, and the cable just snapped. We're falling, but at a perfectly constant speed, v0. We'll call the normal Earth frame k, and our new falling frame k prime. So how different are these two views? Well, in frame k, on Earth, the ground is still and the stone picks up speed from 0. But in our falling frame k prime, which is moving down at that constant speed v0, well, the situation looks completely different. Let's see just how different. Now, to switch between these two viewpoints correctly, we can't just wing it. We need a tool. And since we're dealing with speeds way, way slower than the speed of light, we can use what's called the Galilean transformation for velocities. This is our key to translating the physics from one frame to the other. The rule itself is actually pretty simple. The velocity in our new frame, which we'll call v prime, is just the original velocity, v, minus the velocity of our new frame itself, which we'll call v. And just to keep things consistent, let's define the downward direction as positive. That means our frame's velocity v is a positive v0. Okay, let's put this tool to work and see what this whole event looks like from inside our falling frame. We have to be careful though. We need to transform the velocity of every single thing in the problem. The stone at the very beginning, the Earth itself, and the stone right at the end at the moment of impact. So just to be super clear, we are now watching everything from a frame of reference that is moving downwards at a constant speed, v0. Now, because this frame is moving at a constant velocity, it's not accelerating, all the laws of physics, including the acceleration due to gravity, g, are exactly the same. That's a really important point. First up, let's transform the stone's initial speed. In the Earth frame, it was 0. So in our new frame, that becomes 0 minus v0, which gives us negative v0. Now, hang on. What does a negative velocity mean here? It means that from our falling perspective, the stone actually appears to be moving upwards when it all starts. Weird, right? Okay, next up, the Earth. In the normal frame k, the Earth's velocity is obviously 0. But in our frame k prime, its velocity is 0 minus v0, which is, again, negative v0. So from our point of view, the Earth itself is rushing upwards towards us at speed v0. And right here, this is probably the #1 mistake people make when solving problems like this. We are so used to thinking of the ground as being fixed and stationary that it's easy to forget to transform its velocity too. But in our new reality, the ground is very much in motion. It's flying up to meet the stone. All right, finally, the big moment, the impact. In the Earth frame, we know the stone's final velocity is v0. So let's transform that. We get v0 minus our frame's velocity, which is also v0. And that gives us 0. Yep. At the exact instant of impact, from our falling perspective, the stone is perfectly stationary. Whoa, hold on a second. The final velocity is 0? How is that possible? It feels like our answer just completely vanished. But this is where you see just how beautiful and consistent physics is. The descriptions of what's happening are totally different, But the physical reality? That's identical. So this is the big question, the apparent paradox we have to solve. If the final velocity is 0, where did our answer, the square root of 2gh, go? Well, let's think about what the problem is actually asking for. It wants the velocity with which the stone hits the ground. That, by definition, is a relative velocity. See, the actual physical event, the crash, only cares about the difference in velocity between the two things that are colliding. It doesn't matter how fast they're moving relative to some random observer. What matters is how fast they are moving relative to each other. So let's calculate that relative impact velocity in our k-prime frame. It's the stone's final velocity minus the Earth's velocity. That's 0 minus negative v0. And what happens when you subtract a negative? The two negatives cancel out, and we get a relative impact velocity of positive v0.
And there it is. We got the exact same physical result. The speed at which the stone actually collides with the Earth is v0, which, as we know, is the square root of 2gh. The physics works perfectly, whether we're standing still on the ground or falling out of the sky. It's all consistent.
And this really demonstrates one of the most fundamental ideas in all of physics. The physical outcome of an event doesn't depend on which inertial reference frame you happen to be watching from. The numbers we use to describe it might change, but the reality, what actually happens, that stays the same. And that leaves us with a really fascinating question to think about. We used a weird reference frame here just to prove a result we already knew. But are there times when choosing a strange, non-intuitive frame of reference can actually make a fiendishly difficult problem suddenly, surprisingly simple? The answer is yes, and it's one of the most powerful problem-solving tricks in a physicist's toolkit.